something which I have to write here now. I end up that my alpha component of a time-dependent dipole moment is the permanent contribution plus 1/2 sum over beta, and now that integral over frequencies from -infinity to +infinity. Now the response function in the frequency domain, mu alpha, and I take the minus sign which I had here, this minus sign, which is the minus sign from up there. I take that in my response function, beta, and then I have the field components, beta, omega, and I have e to the minus I omega t d omega plus higher order terms. And I want to do two things more. I can go back to, the difference between this expression, which is the one I want to compare it with, and that expression is now again that here I have from -infinity to +infinity, and up there I have from 0 to +infinity. And I needed to extend that integration up there for the field in order to really have it as a Fourier transformation. But now I can go back to the original cosine expression. And then I get 0 mu alpha 0 plus sum over beta from 0 to infinity, my response function in the frequency domain with two dipole moment operators, the beta component of the field, cosinus of omega t d omega plus higher order terms. And if I compare that with the expression, the classical expression for the dipole moment, then I can see that this this response function is actually the alpha beta component of the frequency dependent polarizability tensor. So what do you do in order to derive expressions like this, or similar for other properties? Essentially what you do is you have a definition of the property, which is this one here, which is the classical definition. And then you try to recreate that by doing time-dependent perturbation theory until you end up with an expression which looks very much the same and allows you to identify how this alpha, how the polarizability looks like. And here the permanent dipole moment. The permanent dipole moment we knew already for a long time. That is just the expectation value of the dipole moment operator. And then the polarizability is a linear response function. Now, we have an expression for that linear response function here in the time domain. That we know what that, in principle we know what that is. These are our time-independent unperturbed wave functions. I have here a commutator and I have those operators, time-dependent operators. But I haven't said anything yet how that looks in the frequency domain. One short comment before I do that. I mean, all the derivation I did here, I used in a few places that those states are eigenfunctions of those operators. Like we sort of, in a way, always do when we have perturbation theory. We first look at the case for exact states. So this derivation is, again, on the assumption that I actually would know what those exact states are. You can do the completely analog or same derivation also if you do not assume that you have exact states. For example, you can do that with a coupled cluster state, coupled cluster wave function. There are a few things which then obviously are going to be different, but you can do the same derivation, and then you end up directly with an expression for a response function in coupled cluster theory. But let's come back to what is that Fourier transformation really? I mean, how does that look like? I had an expression for the one in the time domain, but how does that look in the frequency domain? I'm not going to do that derivation, how you do that Fourier transformation, at least not in this course, but just write up what that is at the end. So the linear response function in frequency domain and again for exact states. That can be written then, so if I have mu alpha and let's write minus mu beta here, which is a polarizability or component of the polarizability, where this is the component of the dipole moment you're looking at, and that beta is the component in which the electric field component you're looking at. Omega. That can be written if I have exact states, because if I have exact states, then I can do a resolution of the identity. And this then ends up as a sum over all the other states than the ground state. Where I then get something which looks very familiar to something which you have seen before. Like this. And this is almost a second order energy, perturbation theory second order energy term. So it's almost the expression for the, as we had for the static polarizability. The only difference is that we have these frequency dependent terms now in the denominator. If they would be gone, then we would get the same expression as we got as from the second order energy correction. So for the frequency going to 0, we get our time independent perturbation theory expressions. So the time dependent perturbation theory, which I sort of try to illustrate, is completely consistent with the time independent perturbation theory. If I go to 0 frequency, I get the same result. And that means also that all those properties like static polarizability, NMR shielding, NMR coupling constants, and all those properties which are defined as second derivatives of the energy, you can write them as response functions just for zero frequency. Now, this is if I have exact states, meaning the 0 and n, psi 0, psi n, are eigenfunctions of the H0 Hamiltonian. And these are the corresponding eigenvalues, the corresponding energy of those states. And that thing is like in time-independent perturbation theory called as the sum over states, or spectral representation of the response function. Now, it doesn't really tell us yet how to calculate that. Well, we could calculate it precisely as is written up here. We could calculate all the excited states and the energies by solving the unperturbed Schrödinger equation. And we could just stuff it in here, do the summation, and be done with it. That's in most cases not what you want to do. Because we would have to calculate all the states. There are some exceptions where some people actually do that, but in most cases you don't want to do that. So you need another expression of doing that.